I'm a physicist, and today I want to talk about something we've all heard before. People say light is both a wave and a particle. It sounds clever. It sounds modern. But if you stop and really think about it, it's a strange thing to say, because a wave is spread out and a particle is not. So instead of memorizing the phrase, let's slow down and ask what light actually does, and why this idea doesn't mean what most people think it means. Let me start with a quiet question that sounds simple, almost harmless. When someone says light is both a wave and a particle, what do you picture? Most people nod, feel satisfied, and move on. It sounds deep. It sounds like modern physics doing something mysterious. But if you stop and really ask what that sentence means, something feels wrong. A wave is spread out. A particle is localized. Saying it's both feels like saying something is both a cloud and a pebble at the same time in the same way. So let's slow down. Not to be clever, not to sound advanced, just to understand what's actually going on. We'll start with something very ordinary. Light hits a wall and makes a bright spot. That's familiar. Now put a very small hole in front of the light and behind it a screen. Instead of a sharp spot, you get a fuzzy pattern with rings. That looks like a wave spreading out. Water does that. Sound does that. So we say, light is a wave. But now change the experiment. Make the light extremely dim. So dim that only one tiny flash appears on the screen at a time. Each flash is localized. It's a single event. It looks like a particle hit the screen. Here's the strange part. If you let this go on long enough, those individual flashes build up the same wave-like pattern, not because many lights are interfering with each other. There's only one at a time. Each one lands in a specific place, but collectively, they arrange themselves as if a wave were guiding them. It's the point where people throw up their hands and say, okay, it's both. But that's not an explanation. That's a label we use when we stop thinking. Let's ask a more honest question. What do we actually observe? We observe discrete detection events, clicks, flashes, localized interactions. That part is particle-like. But we also observe a pattern in the probabilities of where those events appear. That pattern behaves like a wave. So the confusion comes from mixing two different things and pretending they're the same. One is what happens when light interacts with matter. The other is how we predict the chances of different outcomes. Light itself is not switching costumes. It's not sometimes deciding to be a wave and sometimes a particle. What exists is a mathematical description that tells us the probability of different events. That description spreads out like a wave, but the event, when it happens, is always localized. Does that make sense so far? We're not saying light is half one thing and half another. We're saying the wave is not a physical object sloshing through space. It's a tool for predicting where something might happen. Here's a simple analogy. Suppose I tell you there's a rain cloud overhead. I draw a weather map showing the probability of rain across the city. That map might be spread out, fuzzy, with gradients. But when rain actually falls, it hits one spot on your head. The map didn't turn into a raindrop. The raindrop didn't spread out over the city. One is a description. The other is an event. Light works like that, except the description follows very precise rules. Now, there's another idea that causes trouble. People like to imagine little particles flying along wiggly wave paths, or waves that suddenly collapse into particles. That picture feels comforting, but it adds machinery that isn't there. Nature doesn't owe us a picture that fits our everyday intuitions. All we can say, honestly, is this. There is something that propagates through space according to wave-like equations. That thing gives us probabilities. And when an interaction occurs, we get a single localized result. Calling one part wave and the other particle is just borrowing old words that don't quite fit. Let's test this way of thinking. Suppose light really were a wave in the usual sense, like water. Then if you make it dimmer, the wave should get weaker everywhere. But what we actually see is not nudist splashes everywhere. We see fewer splashes, but each splash is just as sharp as before. That's not how ordinary waves behave. Now suppose it really were a stream of tiny particles then each particle should go through one hole or the other, and there should be no interference pattern when only one particle is present, but the pattern still appears slowly, inevitably. That's not how ordinary particles behave. So light is not failing to decide what it is. Our classical categories are failing to describe it. There's an uncomfortable truth hiding here. The problem isn't that reality is contradictory. The problem is that we're emotionally attached to certain mental pictures. We like to imagine little things moving around in space in familiar ways. When that fails, instead of letting go, we glue the pictures together and call it a paradox. Another uncomfortable truth is that saying both wave and particle often signals the end of understanding, not the beginning. It feels profound, but it prevents sharper questions. Once you accept the contradiction, you stop asking what is actually being measured and predicted. And here's a third one. Many people repeat this phrase confidently without ever checking whether it actually explains anything. It becomes a badge of sophistication. But repeating words is not the same as understanding. So, what should we say instead? We should say that light is described by a quantum mechanical rule that gives probabilities for different outcomes. That rule evolves smoothly, like a wave. And when light interacts with something, the outcome is discrete. That's it. No drama, no dual personalities, just a framework that works. Now you might ask, but what is light really then? That's a fair question. And the honest answer is, we don't know in the way you're asking. Really often means in terms of familiar objects. Nature doesn't promise that everything fits into eaches. We evolved to handle rocks and water. What we do know is how to calculate what will happen. And those calculations match experiments with extraordinary accuracy. If you demand a picture beyond that, you may be asking for something the world doesn't provide. There's a habit of mind that's worth noticing here. When something doesn't fit our expectations, we can react in two ways. We can force it into old boxes, or we can adjust the boxes. Progress usually views from the second choice. So the next time you hear that light is both a wave and a particle, pause. Ask yourself what that sentence actually explains. Ask whether it predicts anything new. Ask whether it's pointing to a real mechanism, or it's smoothing over confusion. Understanding often improves not by adding ideas, but by removing the wrong ones. And if you walk away with just one thing, let it be this. Nature is not obligated to make sense in the language we're comfortable with. Our job is not to defend our favorite metaphors, but to follow the evidence carefully, even when it leads somewhere unfamiliar. If you do that slowly and honestly, the world starts to feel less mysterious in the fake sense, and more fascinating in the real one. Let's keep going, because this is exactly the point where people usually stop too early. Once you accept that the wave is a rule for probabilities and not a physical ripple of stuff, another question appears, a quieter one, but more serious. If the wave isn't a thing, why does it behave so precisely? Why does it interfere with itself? Why do the probabilities add and cancel in such exact ways? This is where the temptation to retreat into mystery is strongest. People say, well, that's just quantum weirdness, and move on. But that's a way of protecting yourself from thinking, not a way of understanding. So let's take it slowly. Imagine you're standing at a crossroads, deciding which path to take. Before you choose, you might weigh the possibilities. You don't physically walk both roads, but in your mind you consider each one. Some paths seem more likely to lead where you want to go, others less. You could even interfere with yourself by changing your mind halfway through. Now, that mental process isn't a thing in the world like a rock or a wave in water, but it still follows rules, and those rules can be surprisingly subtle. Quantum mechanics is a bit like that. It doesn't describe what light is in the everyday sense. It describes how possibilities evolve. And here's the key idea that often gets lost. Possibilities don't combine the way actual events do. They combine with phases, with signs, with cancellations. That's why you get interference. When two possibilities lead to the same outcome, you don't add their probabilities directly. You add something more basic, and only at the end do you calculate a probability. That's why you get dark fringes where you might expect light, and light where you might expect darkness. This isn't because light is confused. It's because possibility is not the same thing as actuality. Now pause and ask yourself, does that actually make sense? We're used to thinking that only real things matter. But before something happens, there are many ways it could happen. And the structure of those possibilities affects the final result. That idea feels strange only because we're not used to treating what could happen with the same seriousness as what did happen. But nature does. Another common misunderstanding sneaks in here. People hear that observation affects the outcome, and they imagine consciousness reaching into the world and changing it. That's a dramatic story, but it's unnecessary. What really happens is simpler and less mystical. When light interacts with something that can record which path it took, the different possibilities stop being able to interfere. Not because someone is watching, but because the information is now spread into the environment. Interference requires ignorance. In a very precise sense, if the world contains a record of which alternative occurred, the alternatives can no longer combine. That's not philosophy. That's physics. You can test this. Set up an experiment where in principle you could know which path the light took, even if you never look, even if no human is involved. The interference disappears. So the wave-like behavior isn't about awareness. It's about whether possibilities remain genuinely open. Now let's confront another uncomfortable truth. Many explanations of quantum mechanics fail because they try to make us feel comfortable instead of accurate. They replace one mystery with a friendlier sounding one. But understanding doesn't mean emotional comfort. It means internal consistency. If you're willing to tolerate the idea that the basic object of the theory is not a thing, but a rule for possibilities, much of the confusion dissolves. Still, there's a lingering urge to ask, yes, but what is really traveling through space? That urge comes from our everyday experience. In daily life, something either goes here or there, it has a path. It occupies a place. Those intuitions work extremely well at our scale. But here's another hard truth. Nature does not scale our intuitions down politely. At very small scales, the rules change. And if you insist on forcing small things to behave like big things, you'll stay confused. Instead, you can adopt a different strategy. Don't ask what light is like. Ask what light does. Ask what can be predicted and how accurately. When you do that, quantum mechanics stops being a collection of paradoxes and starts being a remarkably clean system. It tells you how to calculate the chances of outcomes. It tells you how those chances evolve. And it tells you what happens when systems interact. It does not tell you a comforting story about tiny billiard balls or rippling fluids. And that's okay. There's a lesson here that reaches beyond physics. We often confuse explanations with metaphors. Metaphors are useful, but only up to a point. When you forget where the metaphor ends and reality begins, you get stuck. Calling light a wave helped for a while. Calling it a particle helped for a while. Calling it both helps socially, because it sounds advanced. But it doesn't help intellectually. Real understanding often requires giving up a good metaphor without having a better one ready. That's uncomfortable. People resist it. They'd rather hold on to a bad picture than no picture at all. But the absence of a picture is not the absence of understanding. Sometimes it's the sign that you've reached the edge of what pictures can do. Let's bring this back to something concrete. If you shine light through two slits, the pattern you get is not telling you what light is. It's telling you how the probabilities are structured. The pattern is a map of possibility space, revealed one dot at a time. Each dot is real. Each dot is localized. But the pattern is not made of dots. It's made of rules. And those rules are the same whether you send 1 unit of light or 1 trillion. They don't care about your intuition. They don't care about your metaphors. They just work. So when someone says light is both a wave and a particle, you can hear it differently. You can hear it as a historical compromise, a way of bridging old ideas while we learn better ones. But you don't have to stop there. You can say more precisely that light is quantum mechanical. And quantum mechanics doesn't describe objects the way classical physics does. It describes the structure of possible events. That statement may sound less poetic, but it's more honest. And honesty matters, especially in science. Not because it sounds noble, but because it prevents self-deception. The biggest mistakes don't come from ignorance. They come from thinking you understand when you don't. If you can sit with that discomfort, if you can resist the urge to simplify too quickly, something interesting happens. The world stops looking contradictory and starts looking subtle. Not mysterious in a mystical way. Mysterious in the way a deep game is mysterious, where the rules are simple but their consequences are rich. And that's a good place to end up. Not with slogans, not with paradoxes, but with a clear sense of what we know, what we can calculate, and where our everyday language quietly breaks down. That's not the end of curiosity. It's the beginning of thinking more carefully. And in the long run, that's what actually pays off. Let's push a little further, because there's still a subtle trap waiting here. Even after people accept that the wave is a rule for probabilities, they often smuggle the old picture back in through the back door. They say things like, okay, it's a probability wave, but surely something real is waving underneath. That sounds reasonable. It feels cautious. But it quietly reintroduces the same confusion. So let's examine that impulse carefully. Why do we want there to be something underneath? Because in everyday life, rules usually describe things. The rules of traffic describe cars. The rules of chess describe pieces. So it feels natural to assume the rules of quantum mechanics must describe some hidden object moving around. But that assumption is not guaranteed. It's a habit, not a necessity. Think about temperature. Temperature is real. It affects what happens. But it's not a tiny object hiding inside matter. It's a summary of motion. Asking what is temperature made of is the wrong kind of question. You don't find a little temperature particle if you look closely enough. Quantum states are similar. They are real in the sense that they predict outcomes reliably, but they are not things you can point to in space like marbles. Now here's another uncomfortable truth. Many long arguments in physics are not about experiments at all. They're about language, about what kinds of questions we insist on asking. If you demand an answer to what is really there in classical terms, quantum mechanics will disappoint you. Not because it's incomplete, but because the question assumes a structure that nature doesn't use. Instead, quantum mechanics answers a different question extremely well. Given this situation, what can happen and with what likelihood? That shift in question is easy to miss, but it changes everything. Let's test this way of thinking with a familiar puzzle. People often ask how light knows whether one or two slits are open. That question sounds clever, but it's misleading. Light doesn't know anything. There's no decision being made. What changes is the structure of the possible paths. When both slits are opened, there are more alternatives that can contribute to the same outcome. When one slit is closed, those alternatives are gone. The pattern changes because the set of possibilities changes, not because light is checking the apparatus. Once you see that, the mystery softens. The drama drains away. What remains is a very strict bookkeeping system for possibilities. Another place people stumble is randomness. They hear that quantum mechanics is probabilistic, and they imagine sloppiness or ignorance, as if probabilities mean we just don't know enough yet. But quantum probabilities are not like rolling dice in the dark. They're precise. They're the most accurate predictions ever tested in science. There's a difference between unpredictability and disorder. Quantum mechanics is unpredictable in individual events, but exquisitely ordered in the statistics. That's another hard truth. You can have perfect laws without perfect predictability, and you can have unpredictability without chaos. Once again, our everyday intuition leads us astray. Now let's look at something even more delicate. People sometimes say, well, maybe light really is a particle, but we just can't know its exact position and motion at the same time. That sounds like a limitation of measurement, but it's deeper than that. The problem is not that light has a precise position and motion that we fail to discover. The problem is that those concepts cannot both be sharp at once. They are not simultaneously well-defined. This is not a statement about technology. It's a statement about the structure of the theory. Trying to force light into the mold of a classical particle leads to contradictions, not because we lack cleverness, but because the mold doesn't fit. At this point, it's worth asking another quiet question. Why do we keep insisting that reality must match our preferred categories? There's a psychological reason. Categories help us think quickly. They save effort, but speed comes at a cost. When the world doesn't match the category, we either slow down and revise the category, or we distort our understanding. Most people choose distortion, not out of malice, but out of habit. That's why phrases like both wave and particle survive. They allow us to stop thinking while feeling informed. But if you care about understanding, you have to be willing to stay in the uncomfortable middle ground longer than most people. You have to keep asking, does this actually explain anything? Now let's revisit interference one more time, because it's the heart of the matter. When two possibilities interfere, they don't cancel because something physical collides. They cancel because of how the rules combine information. This is not unique to physics. It's a general feature of systems where alternatives are tracked with phases. Music does this. Two sounds can cancel without any object being destroyed. The silence is not a thing. It's a result. Interference patterns are like that. They are not made of stuff. They are made of relationships. That's why trying to imagine light as a tiny object, splitting itself and recombining, leads to confusion. You're treating relationships as objects. Once you stop doing that, many paradoxes disappear. Now, someone might object and say, this sounds like you're avoiding the question of what exists. But that objection assumes existence must mean object in space. That's a philosophical commitment, not an experimental result. Quantum mechanics expands the list of what we're willing to treat as real. It says that rules, symmetries, and probability structures are not just bookkeeping tricks. They are part of how the world works. That idea takes getting used to. But once you accept it, you stop fighting the theory and start using it. And when you do, something remarkable happens. The same framework that explains light also explains electrons, atoms, chemistry, and the stability of matter itself. This is another clue that we're not dealing with a patchwork of metaphors. We're dealing with a deep unified structure. If light were really a confused hybrid of wave stuff and particle stuff, it would be hard to imagine such consistency. But if light is governed by a single coherent rule, the consistency makes sense. So the right question is not, is light a wave or a particle? The right question is, what kind of rule governs light's behavior? And the answer is a quantum rule. That rule doesn't fit neatly into our old categories, because those categories were built for a different scale of reality. There's no shame in that. Every generation inherits concepts that eventually break. The mistake is clinging to them after they've stopped working. So when you hear simplified explanations, treat them gently but skeptically. Ask what they leave out. Ask what they prevent you from asking next. Understanding is not about memorizing strange facts. It's about knowing where your ideas apply and where they don't. And if there's one habit worth cultivating here, it's patience. Patience with confusion. Patience with incomplete pictures. Patience with the fact that reality doesn't rush to meet our expectations. If you can slow down, resist slogans, and follow the logic step by step, light stops being a paradox. It becomes something quieter and more impressive, not a thing pretending to be two things, but a reminder that the universe is under no obligation to be simple in the ways we prefer.